So from part 2 of 4, recall this last Laplace transformation that we undertook. So where we went from converting these first order and second order differential equations here into the equivalent equation, but in the complex frequency domain that's used for Laplace. Well, the transformation then moves from the time domain into the complex frequency domain. So just as a recap, d by dt that you can see here on this equation here effectively becomes s. D squared dt squared effectively becomes s squared. And then likewise here you can see this d over dt here becomes s here. And obviously we've got the leading coefficient here of 3. Outside the brackets on each of these you'll see y of s, because y of s is obviously common for each one of these, where y of s is your output. So just recall y of t, when we undertake the Laplace transformation, just becomes y of s. And then likewise for the input, which is here is u of t for the first order, and 4u of t for the second order, becomes capital U of s and 4u of s. So as I told you in part 1 of 4 of this series of videos, the Laplace transformation enables us to algebraically manipulate the equation using formal rules of algebra to effectively put this into the transfer function form that is used in control systems, or when we're mathematically modeling a system using continuous time mathematics, which is using the Laplace transformation. So the form of a transfer function for a system is given by this equation. So equation 2.5, where g of s is equal to y of s over u of s, which is effectively a ratio of output over input. So straight away, u of s, as I've previously told you, is the output, u of s is the input, so you can probably already see how, using formal rules of algebra, so just to basically manipulate these equations, division, multiplication, how you could rearrange that to put it into this y of s over u of s. Then in terms of pictorial form, you can see here continuous time system g of s, and I'll just note g of s is the general notation that is normally used, not all in all cases, but it's quite normal to use g of s to effectively for the notation for the system. So g of s here, and this line here represents a signal, so u of s, so effectively u of s here, and then y of s here, so input and output, and then the green block here, output over input, that would be your transfer function. Okay, where when we go on to block diagram algebra, you'll see that y of s is effectively u of s multiplied by g of s. But don't worry. So if we now move on to an example and consider these first and second order Laplace transformations that we saw on the previous slide and also in part 2 of 4. So what we will now want to do is convert these into the transfer function form. So to rearrange this first order equation here in the Laplace domain into transfer function form, so using equation 2.5, so if you recall equation 2.5 in the previous slide was effectively just y of s over u of s, and that there's your transfer function. What we want to do is multiply first of all by 1 over s plus 2, because what I told you is we can effectively rearrange the equation just using formal rules of algebra. So if we multiply it by 1 over s plus 2, we'll end up with this equation here, y of s is equal to u of s over s plus 2. Obviously you have to multiply that by both sides, and then if we then multiply it by 1 over u of s, what we'll then end up with is y of s over u of s, and obviously u of s is going to cancel u of s, so 1 over s plus 2, and that there is our transfer function. What you'll notice here is rather than use g of s, the notation I've used here, I've used g subscript a, because originally, if you remember when I gave you this ODE in video 1 and part 1, and we've also used this in part 2, I told you that this was for the actuator. So the overall notation here is g of s, but because I'm using a transfer function as part of the actuator, which makes up the system, I've used g subscript a of s. Then if you move on to the second order, so it's exactly the same process, and you're probably starting to see that these are actually quite straightforward. So again, if I use the whole idea referring to equation 2.5, cross multiply by 1 over s squared plus 3s plus 4, so I'll end up with y of s is equal to 4 u of s over s squared plus 3s plus 4. Then again, if I then multiply both sides by 1 over u of s, so then I'll end up with y of s over u of s is equal to 4 over s squared plus 3s plus 4. And again, the notation I'm using here is g subscript p, because what this original ODE we were using it for was to effectively mathematically model the process. At the moment, obviously, this is just a general actuator and process. I'm not applying this to any application at the moment, but the intention of these videos is just to really show the process of going from the ODE to the transfer function. What you will notice is you'll probably think, well, u of s, yeah, that makes sense. Okay, for the actuator, as you can see obviously here. And then what you're probably thinking is, well, I haven't put any notation here. Okay, the reason why I haven't done that there, because it gets a little bit messy, because the output from the actuator is y of s, and then the input to the actuator is u of s, which kind of like is y of s from the actuator. So for now, I've just ignored that, but you'll notice that y of s here I've used for the notation for the output of the process. So don't be too worried about that. I've just left that off there just to kind of avoid any sort of confusion. So what you've seen in this video is the quite straightforward transformation. Once you've done the Laplace transformation, how we can then quite easily algebraically manipulate the equation to then put the transfer function into, to put the equation into the transfer function form, which, as I told you in part 1 of 2 of the videos, is one of the big reasons and one of the main kind of reasons to use the Laplace transformation, because it enables us then to mathematically model closed loop control systems, or systems as part of a closed loop control system, in block diagram form, which is effectively in the continuous time domain, which is the bread and butter of what we use in control systems or control design.